purpose of flow in a reef aquarium, as we understand it, is to efficiently transport nutrients, food, and oxygen to the reef inhabitants, as well as to carry away metabolic waste products. In the confines of an aquarium, the flow pumps must be able to efficiently produce a ring current, one that carries from one end to the other, that will lift and suspend detritus and carry it to the filtration units. Ideally, the direction of this flow is alternated to minimize the formation of sediment and constant eddies generated by reef obstacles interacting with the flow. The flow in a coral reef has velocities ranging from 0.2 meters per second in a protected lagoon to as high as 3.9 meters per second in a surge channel. Despite what some have been led to believe by only viewing a conclusion and accompanying bar graph, there is no simple meter that measures liters per hour. Instead, flow is calculated by mathematical analysis, and the output of a pump can generally be divided into two products, flow and turbulence. What flow meters measure is velocity. In the case of wide flow pumps, an average velocity of the cross-section of the output is taken, and this is factored with the diameter of the flow area to produce an estimate of the flow in liters per hour. Such an estimate has a margin of error. While flow is a directional kinetic energy, turbulence is an unsteady, rotating kinetic energy, a vortex or eddy, for example. It has a high velocity compared to laminar flow, but lacks direction. These turbulent forces are shown by flow meters as widely varying readings. A more laminar flow produces a far more constant reading. This is not to say turbulence has no value. It is extremely effective at mixing and gas exchange. It is a necessary force for disrupting the diffusion boundary layer at the coral structure for efficient transport. However, propeller pumps by nature produce turbulence due to the rotation of the flow, and turbulence is also induced downstream at every intersection with a static object, including the water itself. A well-designed pump should produce only enough turbulence to accomplish this goal without excessive losses of the kinetic energy to produce the required reach of flow. In this video, we will demonstrate the flow produced by our pumps, which correct for the turbulence forces versus those of a competing model controllable pump, whose design produces far more turbulence. Comparisons are based on advertised flow rates. We show the flow utilizing a UV indicator dye, 20 milliliters per demonstration. The aquarium is 150 centimeters by 60 centimeters by 60 centimeters with 12 millimeter thick float glass, and it is illuminated by 60 watts of UV light. It should be noted that transport of dye is an ISO standardized test and is regarded to have an uncertainty of 0.5% when properly performed. This method calculates laminar flow velocity by the time it takes a weak radioactive tracer dye to arrive downstream. While we did not have a sufficient tank length nor access to the radioactive tracer dye required to do the ISO standardized test, we do hope that further independent analysis of flow will utilize this method, and the video presentation effectively demonstrates where there may be errors from relying on standard flow meters for measuring propeller pump flow. We have also included a visual of the flow by adding bubbles in which you can see the turbulence, flow rotation, and losses due to recirculation of flow output, where a pump consumes a portion of its own flow. The air was injected by a Shago M2K3, and the output was not adjusted or modified between the various demonstrations. We superimposed this video over the reading of an RCI Clima Air 5 with Microwater 5 propeller probe. While the different method results in slightly different readings from previously published flow studies, the results are largely consistent. Varying methods of measurement do result in variation, and a propeller-based probe results in drag and resistance and would inherently give lower readings. But this effect is consistent, and we are not calculating flow, only demonstrating the turbulence forces present and the quality of the flow. The probe was placed one output diameter from the pump, dead center in the output, and the reading labeled V is an instantaneous reading, while X is a 10-second average. We feel the ideal is that V is stable and closely correlated to X. In all cases, the pumps were stock versions run at 100% of output power.